In this video I will talk about the gradient. Now I will start by showing you what is the definition of the del operator. This is the del operator. So the del operator is a vector. Okay, I have the vector sign here, and it is defined now in the Cartesian coordinate system as x hat. So this is the x unit vector times the partial derivative with respect to x. Okay, there is nothing here. It's the partial derivative with respect to x. This is just an operator, so I need to leave this empty. Plus y hat, the unit vector in the y direction, times the partial derivative with respect to y, and the same thing in the z direction. Now, this is an operator, and that means that I have to, I cannot really do anything just with this. I have to apply the operator to a function. So, let's say that I have a function f that is a function of x, y, and z. Now, if I take the operator and I apply it to function f, this is when you see this, practically this means that you apply the del operator to the function f. Okay, this is what I'm doing over here. I'm applying the del operator to function f. Now, when I apply the operator, if I use the definition of the del operator, so I'm just copying what I had there. I want to show you for this first time how you will be doing it. Then this is times the function f. What this will give you is x hat, the partial of f with respect to x, plus y hat, the partial of f with respect to y, plus z hat, the partial of f with respect to z. So this is what you get when you apply the del operator to a function. Now, I want to remind you, the del operator is a vector, and when you apply it to this scalar function of x, y, z, at the end you have a vector. This is your vector. This is the x component. This is the y component. That's the z component. If you want, I can write. I can use the bracket notation to show you what that looks like. Okay, so I have my x, y, and z components. This is what you get when you apply the del operator to the scalar function f. These are your x, y, z components. Now, this is a vector, and I can also mention at this point another vector, the displacement vector. And this is given as dx times x hat plus dy times y hat. Okay, this is times plus dz times z hat. This is also a vector. This is the displacement vector. Now, I want to show you what happens, what you get when you find the dot product. Now, this is the dot product between the del operator applied to the function f dot dl. Okay. Now, I want to remind you here, every time you find the dot product between two vectors, the result is the x component of the first vector times the x component of the second vector plus the y component of the first vector times the y component of the second vector, and the same thing in the z. So the x component of this is the partial of f with respect to x. The x component of dl is dx. and I do the same thing in the y. And the same thing in the z direction. Now, this is, okay, I want to point out, this is the dot product between two vectors. And we know that anytime you find a dot product, the result is a number. And this is a number. This is a scalar. Whereas, I want to point out before here, let's use this. This was a vector. Okay, when you apply the del operator to a function, you get a vector. The dl, okay, let's say here, let's say this is also a vector. Okay, vector dot product with a vector. At the end, you get a scalar, a number, as you should when you take the dot product between two vectors. Now, I want to mention, this is the change of the function. This is the partial of f with respect to x is the slope of the function if you do a small change in the x direction times a small change in the x direction, and the same thing in the y and z. This will give you the total change of your function f. Now, this is a little bit difficult to visualize in 3 dimensions. So what I'm gonna do, I'm gonna copy this on another board, and then I will show you. I will interpret that in 1 dimension to help you interpret this in 3 dimensions. So what I found is that the del operator applied to the function f dot dl will give me the total change in the function f. And what I mean with that is that I have the partial of f with respect to x times dx plus the partial of f with respect to y times dy plus the same thing in the z. Now, I want to show you how you can interpret this, but I cannot do it in 3 dimensions. Okay, I'm going to have to show you the interpretation of this in 1 dimension. So, say this is the x, this is my function x, and let's say that this is my function. Now, the partial, anytime you have a derivative, you can, in the graphical representation, the derivative is the slope of your graph. Now, how can I find the slope? We know that we find the slope by finding the rise over run. So if I go here, if I have, okay, for a small change in x, this is, if you want, this is the run. For a small change in x, what I can get, let's say if this projects here and that projects there, and then I find the projections of those two here on the vertical axis where f is, then sorry, this will give me the rise. This will give me the small change in f that I get if I make, okay, and well, oops, I'm a little bit, I missed. And all right, I missed this by a little bit. So the rise is what I get, the small change in the function f that I get when I make a small change in x. Now, as I said before, this is the slope. So if you take the slope, which you can calculate by doing the rise over run, now I also want to mention this is the partial derivative of f with respect to x. This means that we are talking really about an infinitely small infinitely small change in x. Okay, these are very small change in x, a very small change in f. If you take the slope and you multiply it really with how much you're changing your x, you can get the change in your function. So I can find by how much the function f changes if I take the slope at the point and I multiply it with how much I'm changing x. So the slope times the small change in x will tell me how much my function f changes as a result of that change in x. Now this is in one dimension how you can interpret this term. Now if your function f is a function of 3 dimensions, x, y, and z, and you do your moving in all 3 axes, the x and y and z, then as a result of making a change in x, you will induce, if you want, a change in the function. But because you're also changing the y, you will also induce a change in your function, and that change in the function is calculated by finding the slope in the y direction times the small change in the y that you want to make, and the same thing in the z direction, in the z axis. So when you're moving in all 3 axes, in all 3 directions, those 3 independent motions will affect the change in the function f. And this is how much your motion in the x direction affects the function f. This shows you how much your motion in the y direction affects the function f, and the same thing in the z. As I said, this is more difficult to interpret in 3 dimensions. So when you start working with a gradient, start in 1 dimension and think about the slope, rise over run, what's the meaning of dx, and what you get with df, and then try to generalize that in your mind in all 3 axes. Now I'm gonna go back to my previous board. And here I want to mention, because the dot product between these 2 vectors gives you the total change in the function f, we call this is what we call the gradient of the function f. So the gradient of the function f by definition is a vector. Don't forget that. Now we know that vectors have 2 properties: direction and magnitude. So from the gradient, so when you have the gradient vector, this vector can tell you 2 things. It can show you, okay, so I said vectors have 2 properties: the direction and the magnitude. As far as direction is concerned, the gradient vector shows you the direction at which the function f has the greatest change. So when you find the gradient vector and you visualize that in your 3 dimensions, the direction at which that vector is pointing is the direction at which you get the greatest change in the function f. And the magnitude of the gradient vector will show you the slope if you move along the direction of the gradient vector. Okay, it will show you by how much your function f will change if you move in the direction of the gradient vector. And this completes everything I wanted to mention about the del operator and also the gradient of a scalar function.